Okay, in this video we're going to finish up logic. We covered the conjunction, now we want to cover the disjunction operator. So in logic, the disjunction, which is the OR operator, is the V symbol. So it's written like that. Of course, it's not going to be like that in R. So any two statements can be combined using this word OR to form a new statement, and that will be called the disjunction of the two statements. So we write it this way, and it's read P. This is read P or Q. And in R, it's either this symbol or the double pipe, and we'll talk about the difference between them. And that also applies to the difference between the ampersand and the double ampersand. So the truth table for the disjunction is like this, and if you compare it with the conjunction, you'll see that the conjunction was true only in the first case and false for the rest of them, whereas the disjunction is false only in the last case and true for the others, which makes sense if you think about the word OR. So if I say Tokyo is in Japan, or 1 plus 1 equals 2, you would say that's a true statement. If I said Tokyo is in Japan, or 1 plus 1 equals 1, you would still, even though the second part is not true since we have the OR there, you would say that this is still a true statement. The compound statement is still true. In this case, even though the first one is false, the second one is true, so you would say that the compound statement is true. However, in the case when they're both false, then in that case, you would say that the compound statement is false. One remark, and that is that the English word OR is commonly used in two distinct ways. So this, I'm talking about the English word OR, not the disjunction, but the English word OR. Sometimes it means P or Q or both, and sometimes it means P or Q but not both. So the truth table above is for the former, for the case of both. So if both are true, we still say that it's true. But in English, if I say P or Q, I may mean that this one is not true. So you just have to be aware of the English meaning of that. Other languages may not have this issue. The symbol V also also refers to the former. So this symbol refers to this table, not the other interpretation of the word OR. The R operators are the single pipe and the double pipe, and they also refer to the former. So the truth table for P or Q, this should be but not both, would not look the same as the above truth table. This should be but not both. So in the R data frame scenario, we would have a statement like this and a statement like this, and this would be the OR, or the disjunction. And the truth table would look like this, just as we saw it before. And if we ask in terms of sets, we have this statement. So in sets, union is OR, and in sets, intersection is ampersand, or conjunction, or and. So here's the example that we looked at. We ask, how many rows are there, number of rows, in our data frame that have age less than 30? We have this many. How many rows have education equal to tertiary? We have this many. How many rows satisfy the and? In that case, it has to be less than either of these, and it's this many. And here, if we ask how many rows satisfy this one or this one, then it's going to be more than this number, and it turns out to be this number. And this is the double pipe, which we're going to explain later. So here's the explanation or on the difference between the single operator and the double, the single and the double. The shorter ones are vectorized. Those are the ones we've been working with, this one and this one, meaning they can return a vector like this. So here, if we take this vector and we say, is it greater than or equal to 0? It's going to compare each term. So the first term is false, the second term is false, the third term is true, the fourth term is true, and the fifth term is true. On the other hand, this one, we have the first term is true, the second term is true, the third term is true, the fourth term is false, and the fifth term is false. And when we use the conjunction, we get the results of that as a Boolean vector. So the longer form, that is this one, evaluates from left to right, examining only the first element of each vector. So it just checks whether, so in this case it would just check, is -2 greater than or equal to 0? And is -2 less than or equal to 0? And together, so one of them is true, this one, and this one is false, but together that gives a false, but it only checks the first one. So it doesn't give back a Boolean vector, it just gives back a single false. So that's the case with this as compared to this, and similarly with this as compared to this. So this one will only check the first elements of each side, so here versus and here, and it will return, it'll be the disjunction operator on those two. Okay, just a small note that has nothing to do with logic at all. It's just a note that I just put in here. You will notice a difference inside a function. So what's the difference between this and this? So if you use this, it's not recommended that you use this inside a function. So here's the difference. So suppose I use this function, median of x equals 110. And then I print x. So x doesn't exist. It was defined inside the function, and so it's not defined outside the function. So if I try to print x, this is actually should be on a second line, but if I try to print x, it won't know what x is. I defined x inside the function. So in this case, x is declared within the scope of the function, so it does not exist in the user workspace. On the other hand, if I do it like this, which we would think would be the same, but it does have a slight difference, because now if I ask for x later on, it is defined, it's equal to this vector, it's equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case, x is declared in the user workspace, so you can use it after the function call has been completed. So that's the difference between this and this. And then I also mentioned, or it's also mentioned down here, that there's a shortcut for typing this, and that is you use the Alt key and the hyphen. That will give you this. So if you don't want to use two keys one after another, you can do it like this. Okay, that's in RStudio. Okay, the negation, and it's written like this. In R we use the symbol exclamation mark. So given any statement P, another statement called the negation of P can be formed by writing it is false that P before the P, or sometimes by using the word not. So sometimes you can use the word not, or you can just say it is false that P is true. So you can write it like this. some other textbooks write it like this. This is for the logical symbol, and this denotes the negation of P and is read not P. So for example, Tokyo is in Japan is P, then not P is Tokyo is not in Japan, or it is false that Tokyo is in Japan. Example, 1 plus 1 equals 1 is P, then not P, it is not true that 1 plus 1 equals 1. And you can see that if P is true, then not P is false, and if P is false, then not P is true. For example, here P is true, not P is false. Here P is false, not P is true. The negation operator in a data frame is this symbol, the exclamation mark. So here we have age is less than 30, and we get a bunch of falses. But if we do not, means age is not less than 30, and we get wherever it was false, it becomes true. So here I just used the head function, so I only got the first 6 results, and they were all false. So the first 6 results with this will all be true. Here, if we have education equals tertiary, it was true, false, 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 true. So not education equals tertiary is false, true, 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 false. So they're just reverse, from true to false and false to true. Okay, in logic, just to let you know that in logic there are other symbols. So we have this one. This is also for and. This is also for and. So these are 3 different ways that you'll see and expressed besides this one. Okay? And for or, this way, you'll also sometimes see this instead of this. Okay? We're not doing logic, but I just thought I'd bring these up. And for not, you can sometimes see it as prime, P prime, or this one are alternatives for this. Okay, one more, and that's the if-then statement. P arrow Q, or P implies Q. This is called the antecedent, and this is called the consequent in this if-then expression. It's expressed in normal English as if P then Q, P implies Q, or Q only if P. So let's take an example where, let's go to here. So you can see that the only time this is true, the only time this is false is if this is true, the antecedent is true, and this is false. For example, suppose we represent the statement today is Monday by P, and we represent the statement I have algebra class by Q, then P arrow Q can be said in English as if today is Monday, then I have an algebra class today. Notice that both P and Q are statements, i.e. they can be either true or false, but not both. In other words, this is a statement, today is Monday, and this is a statement, I have an algebra class today. And we combine them, and this gives us a compound statement. Okay, and then we have logical equivalence. So if you consider the truth table for not P or Q, so how do you find the truth table? The way you find the truth table for not P or Q is first you write the most basic parts, that is P and Q, and express all the possibilities for the truth values. In this case we only have 4. Then you put in another column for whatever else is in the expression, so not P is also in the expression. So I put in not P, so if P is true, then not P is false. If P is true, then not P is false. P is false, true, false, true. And then instead of comparing these two, because that's not what this says, it doesn't say use these, doesn't say combine P and P or Q, it says combine not P or Q. So compare these two. So using the disjunction or operator, so I get true or false is true. False or false, that's not true, it's false. True or true is true. False or true is true. So the truth table for this statement is here. Now, does that look familiar? Well, if I go back to the previous screen, true, false, true, 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 false, true, true. So for the same set of truth values, P and Q, I get the same result here for this one as I did for if P then Q. So in the case where you have the same truth values for a statement, say this statement versus this statement, we say the statements are logically equivalent. That is, when the P and the Q have the same truth values, we get the same result for this as we do for this. So we call those logically equivalent. So what that means is, if you have this statement, you can always replace it by this statement. Or if you have this statement, you can always replace it by this statement. This is the same as this table, i.e. the final results are the same for each combination of P and Q. We say they're logically equivalent. So in our previous example, we had this: if today is Monday, then I have an algebra class today. That can be replaced by, or it's logically equivalent to, today is not Monday, or I have an algebra class today. So you can sort of think about that and make sure it makes sense in your own mind, but it does make sense. Okay, then there's a little bit more in logic, and these are called the laws of algebra of propositions. This is just a partial list, but these can all be proved using truth tables. Now, some of them seem completely obvious, and they are, but they can be useful when you're trying to analyze things using this so-called logical calculus. What we've been describing is sometimes called the logical calculus. It's kind of like an algebra, right? What we've been doing with these P or Q and all of that. So it's sometimes referred to as a calculus, logical calculus. And these next statements, some of them being super simple, but they can be useful. It's like saying, for example, 1 times A equals A. In mathematics, 1 times A equals A is very simple, but it can be useful. And in the same way, we have P or Q is equivalent to P, and P and P is equivalent to P. That's called the identity. We have P or Q is equivalent to Q or P, so you can switch the order, and the same thing with the N. P and Q is equivalent to Q and P. By the way, this means logically equivalent. There's triple equal sign. Then we have something called the complement. P or not P is always true, and P and not P is always false. Double negation, not P is equivalent to P. Associative, P or Q or R. So doing these two first and then this one is logically equivalent to doing these two first, that is P or Q first, and then R. Distributive, this one is the same as this one. Logic, by the way, what do we mean by all of these equivalencies? When I say this is equivalent to this, I mean they have the same truth table. So you can prove these with truth tables. And this is another form of distribution. It's very similar here and here. So the De Morgan's laws, these are actually useful and not so obvious. Not P or Q is logically equivalent to not P and not Q. Now, you saw that some of this can be used in our R context, so these might be useful at some point. Here's another form of De Morgan's laws. Equivalence of contrapositive. So P implies Q is the same thing as not Q implies not P. So you can substitute in some statements like If I live in Beppu, then I live in Japan. If I don't live in Japan, then I don't live in Beppu. And this one that we just saw, this is the only one that we actually proved. We showed the logical equivalence of this statement and this statement. Okay, we have finished with logic, and now finally we get to probability, and from there we'll work out the naive Bayes algorithm.